So the next talk is by Oliver Grah with the Nooksack tribe to look at a little bit downstream from the glacier.
Thank you. We appreciate this opportunity to present this paper on glacier runoff impact on stream temperature and discharge in the headwaters of the Nooksack River. My name is Oliver Grah, and this is going to be co-presented by myself and Jezra Below, who both of us work for the Nooksack Indian Tribe Natural Resources Department. This paper was originally going to be presented by Dr. Morey Pelto, professor of geology from Nichols College in Massachusetts, who's been monitoring glaciers in the North Cascades for about 30 years. He was unable to make it. The interesting thing is the technical content of the presentation that he had developed doesn't present on his 30 years of monitoring data. It actually looks at inferences on glacier behavior from existing USGS and SNOTEL data. And so because this project is being partially conducted on behalf of the Nooksack Indian Tribe to help the tribe solve climate change impact issues, I thought I'd take a moment just to quickly give you a background on the Nooksack Indian Tribe. The tribe occurs in northwest Washington in an area about 12 miles east of Bellingham and about 15 miles south of the Canadian border. The reservation itself is located in Deming. It's only about 2.2 acres in size, about 1,000 acres of trust lands, very small. However, the usual and accustomed area, that is the area that the tribe has legal right to gather natural resources, is about 720,000 acres, including about 428 acres of shoreline. And the most prominent feature in the Nooksack River watershed is Mount Baker, the Sisters Range, Mount Shuckson, and the crest of the western part of the North Cascades. The tribe relies on harvestable surpluses of Pacific salmon for ceremonial, heritage, subsistence, and commercial uses. Salmon are currently and will continue to be stressed by climate change impacts, including altered stream flows and temperature. Huge efforts are directed towards in-stream restoration to enhance salmon recovery. Other watershed restoration actions will be necessary to ensure persistence and continued recovery of Pacific salmon. The tribe has initiated a climate change project aimed at evaluating the impacts of climate change on the hydrology of the Nooksack River and salmon habitat and survival. This information is needed to plan for effective habitat restoration measures that address the additional stresses of future climate change. And our climate change project will also address water resource management issues of other water users in the Nooksack River Basin. So it's not just a tribal-centric climate change project. With that, I will turn it over to Jezra Below, who will be presenting more of the technical content of this presentation.
Thank you for that introduction, Oliver. So the Nooksack watershed, I believe Oliver mentioned, is in Whatcom County, right outside of Bellingham, Washington. It consists of three main forks, the North Fork, Middle Fork, and South Fork, that all drain into this lower sub-basin that then flows out into Bellingham Bay. And so the headwaters of the three forks drain various amounts of glacier coverage, either from Mount Baker, Mount Shuckson, or the Twin Sisters Range, which is not labeled here. So I'm going to zoom in on the headwaters of the three forks. This is from the glacier database developed by Andrew Fountain and his graduate students at Portland State University, which is an excellent database for all of the glaciers in the western United States. It has area, elevation range, and names of all these glaciers. So the North Fork is the most heavily glaciated of the three forks, draining glaciers mostly from the northwest portion of Mount Baker, as well as the northern part of Mount Shuckson. The Middle Fork is kind of moderately glaciated, draining the Deming Glacier and the Thunder Glacier, as well as smaller glacierets, or the larger glacierets on the Twin Sisters Range. South Fork is the least glaciated of the three, with really just perennial snowfields and vestigial ice from the Twin Sisters Range. So if we kind of summarize that, the North Fork has the largest watershed area of all of them and the largest glaciated area. Middle Fork is actually the smallest watershed area, but moderate glaciated area. The South Fork is kind of the medium watershed area, but the least glaciated. But the Nooksack watershed is overall is pretty unique in that it has these three forks that kind of lie on a spectrum from the glacier snow-dominated hydrology to more transitional or rain-dominated hydrology that we would see in the South Fork. And so with continued climate change and glacier loss, we would expect that the hydrology of the North Fork and the Middle Fork are going to look a lot more similar to the hydrology of the South Fork. So our key questions in this study, on behalf of Maury Pelto and the tribe, is how did these warm weather events in recent years affect discharge and water temperature in the three forks? And what are their key differences between the responses to these warm events? Ultimately, we want to get at what is that overall contribution of glacier runoff during late summer stream flow, how that might buffer low flows as well as stream temperature. And then with future research and future modeling, we want to see how that glacier contribution will change with climate change. So glacier runoff, as John kind of went over, is kind of the product of a glacier, of annual ablation, as well as glacier area. And recent summers have shown that there's been a 5 to 10% higher ablation rate in the Nooksack watershed than the 1984 to 2013 average. So combined with a 10% reduction in glacier area over that same period, this yields an actual overall reduction in glacier runoff contribution, despite that higher ablation rate. So continued glacier decline will only lead to further runoff losses in late summer in particular. So for this study, we compared the stream discharge and stream temperature from local USGS gauge stations to the air temperature from a snowtell site in the North Fork watershed for the summers of 2009 to 2013. And so I'm going to kind of go through a few graphs just kind of describing general overall trends between the forks and between the water temperature and discharge. And so just to kind of get you acquainted with these graphs, everything in blue is discharge, and that axis is on the left here. Everything in red is water temperature. That axis is on the right. And then the black line is air temperature. And so also a good way to kind of organize it in your head is that the dark blue and the dark red are the South Fork, and then the lightest blue and the lightest red or the orange is the North Fork, and then these medium blue and red are the Middle Fork. So because we kind of lost our Middle Fork data for the second half of this summer, I'm going to zoom in on the first warm period, just go over some general trends. So during this warm event, we have, generally large increases in the North Fork discharge with this light blue line, as well as the Middle Fork. More moderate so, but still large, much more variability than the South Fork, for instance, which has, very little response, if not even just a very steady decline or decrease in that discharge. Conversely, for temperature, South Fork has the, greatest increases in temperature and the greatest temperature overall. And then the North and Middle Fork temperatures are very attenuated relatively. So if we break that down by fork, the Middle Fork over here, just kind of moderate discharge changes as well as moderate temperature changes during that period. And then the North and South Fork are kind of mirror images of each other. So, or I guess they're kind of opposite of each other. So the North Fork discharge has much greater variability, much greater values, and very little response in the temperature. And then the South Fork has much greater responses in temperature, but very little response, if not just a steady decrease in the discharge. So, all right, so 2010, very similar trends to 2009 overall, where the South Fork, lowest discharge overall, highest temperature, The North Fork has the highest discharge and the lowest temperature, and then the Middle Fork's kind of in between there. So that's kind of that spectrum I was talking about. But overall, the Middle Fork and North Fork have the comparable variability in the temperature, especially, where that magnitude of change is very much the same. Whereas it's only about 1 degree Celsius, whereas South Fork changes 2 to 4 degrees Celsius for any given warm period, for the most part. 2012 was actually was the warmest and driest of the years that in this study, and same overall trends. But you can see that discharge in all the forks is very low this year. In fact, the Middle Fork, that medium blue line, is actually almost the same runoff amount as the South Fork, which is somewhat unusual. But you can see that there's kind of a, sorry, I lost my train of thought. Well, I'll move on. So I wanted to kind of zoom in on the third warm period, which is a late summer warm period in mid to late September, where you have that steady incline or increase in discharge in both the North and Middle Fork, whereas you have that steady decrease in the South Fork, which is probably indicative of that glacier contribution. Whereas the temperature, South Fork is at least 4 degrees higher than either the Middle or North Fork. And what's interesting is that the Middle and North Fork have almost the exact same water temperature, which is indicative of that glacier melt contribution that's buffering those late summer flows. So 2013, very similar. This was actually the coldest of all of the years. And again, we have Middle Fork and North Fork with that same water temperature in the latter half of the summer. So overall trends to take away from this: South Fork, lowest overall discharge with little to no detectable variability in discharge, but the greatest variability in temperature that exceeds 2 degrees Celsius. The Middle Fork has moderate discharge with moderate increases during those events, and attenuated variability in the temperature that does not exceed 2 degrees Celsius for the most part. The North Fork, greatest overall discharge, greatest variability in discharge, and then the temperature is, interestingly, very similar. Those trends are very similar to the Middle Fork. And so with continued climate change, we would expect both the Middle and North Fork, as they lose their glacier mass, to respond very similar to the South Fork. So of these 12 warm events, the South Fork experienced increases in temperature of greater than 2 degrees for all 12 of those events, whereas the North and Middle Fork only for 2 of those events. For discharge increases greater than 10%, North Fork experienced that for about 10 of those 12 events, Middle Fork for 6 of those 12 events, and then South Fork for 0 of those events. And then this just kind of gives you a gauge of the relative glacier area percent for each fork. So what we do to constrain our glacier contribution to stream flow is that we've been collaborating with Maury Pelto on the Shoals Glacier, looking at measuring mass balance as well as the runoff below the glacier. So here's the Shoals Glacier at the beginning of the summer and at the end with all the exposed ice. So we measure snowpack through probing across the glacier, and then we look at satellite imagery to see how that snow-covered area and ice exposure has changed. So this dark blue area is that ice exposure change. And then we relate that to a stream gauge at the outlet stream, which we've installed these pressure transducers that measure continuous stage in the stream, and then we relate that to discharge measurements to develop a rating curve. So we found that daily ablation rates were about 5 to 6 centimeters per day, and so if we extrapolate that over all of the glaciers in the North Fork, that would yield about 12 to 14.5 cubic meters per second for the entire of glacier runoff in the North Fork. And so this actually is about 50 to 60% of the mean annual discharge in the North Fork, which is a pretty substantial amount of glacier contribution. And so if we look at that over our study period, the change in glacier runoff was only negative 7.3%, whereas the change in the total North Fork runoff was almost 19%. So that this is indicative of how glacier contribution really buffers those late summer stream flows. So just kind of stepping back to more historical context, looking at the main stem of the Nooksack compared to the North Fork, which is the most heavily glaciated. The main stem has decreased since 1971. This is mean summer discharge, and then the North Fork has remained pretty consistent over that same time. Okay, this is the last slide. So, but overall, the glaciers in the Nooksack have kind of followed that same decreasing global trend as the North Cascades and as all of the other glaciers, kind of indicating that widespread glacier loss worldwide. So, we had a few closing remarks.
So, point is, what's the relevance and application of this information? Again, the Nooksack Indian tribe will be using this information to identify climate change impacts on tribal natural resources, identify vulnerability of those resources, i.e. fish, and then develop adaptation plans that are robust in the face of climate change. Our climate change project also involves contracting with the University of Washington, more specifically led by Dr. Christina Bandaragota, to adjust the glacier module to the distributed hydrology soils vegetation model. That work will be used by Dr. Robert Mitchell and his graduate student Ryan to adjust that model specifically for the Nooksack River and update the hydrology of the Nooksack River in the face of climate change. That information will be used to update and modify our habitat restoration plans to be more effective in the face of climate change. That information will also be used by other water users within the Nooksack River. Thank you very much.
Stay close for questions. We do have a couple minutes for questions.
Steve Klein with EPA. I think this is a great story of a tale of three forks. And what strikes me is that in a relatively small landscape, the behavior of the landscape and the dominance of glaciers and the stream flow and temperature is not the same story. And so earlier this morning we talked about more downscaling, more precise climate realizations in order to inform. And while I support that, the interpretation of that downscaled information with the actual physical and biological environment is an equally challenging subject, and one you covered well. Thank you.
Comment but not a question.
Yeah, thank you. This is really fascinating information. I had done some work with my work at ecology and got actually an increasing trend on the North Fork Nooksack for summer minimum 30-day flows. And in some of my trend work, the glaciated rivers tended to be increasing in the Western Cascades, but then I heard a talk a couple years ago by a researcher from British Columbia who said he was seeing decreasing trends on glaciated rivers, which led to a whole bunch of conversations, which is a conversation I hope will continue through these sessions, because apparently, like, whether you see increasing or decreasing trends kind of depends on the mass of the glacier, and there's like a curve as glaciers recede. So I'm just really interested in that topic. And this, it sounds like you're going to have a database. I don't know, it really isn't a question, but just interested in your observations, if you're headed that way, to kind of get some sense of, like, how long do you see increasing flows from a receding glaciers, and when does it start turning into a decreasing flow, or you lose the glacier altogether?
Yeah, that is interesting, because I think that has a lot to do with elevation, because Mount Baker, these these Cascade volcanoes, they have such a large, or not a very large, but that accumulation area, you know, is kind of gaining mass, even though that snow line is kind of increasing in elevation with warming temperatures, there's still that accumulation zone on top. So I guess it depends on the elevation range of the glaciers in the watershed that you're